Okay, as we continue to solve our separable differential equations, in example 4, we have the quantity of x squared minus 9 times the derivative of y with respect to x equals 4 times x times y. Well, our process is called separation of variables, so our goal is to get all the things with x's on one side, all the things with y on the other. Now, there's a couple different routes you can take to do this. I first often like to get the derivative by itself. So I'm going to go ahead and move that x squared minus 9 by dividing by it. So then we'll have dy over dx equals 4xy over that x squared minus 9. And then, good news is that the only thing that has a y is just attached by multiplication on top. So we can technically move that out to the side, right? So then it's a little bit easier for us to see, oh, if we want to move it to the left, we're just going to end up dividing by it. So then we take both sides times 1 over y, remember, is a common way that we're going to think about that. dy, and then how would we be getting rid of dx? Multiplying both sides by it. So we would have 1 over y dy equals 4x over x squared minus 9 dx. Now our variables are separated. We are going to integrate both sides. Left-hand side's nice and easy. It's just the natural log of the absolute value of y. We'll take care of that constant here in a minute. Now the right-hand side would involve some u substitution, or again, you can do a little bit of guess and check. So think about what you have and where. You have almost exactly the derivative of the denominator somewhere in your expression. That's your clue to use u substitution. So if we say, well, okay, if I want my derivative of my denominator to be 2x, right, or that's what it would be, make your numerator into a 2x. And then as long as you remember, well, you had 4 to begin with somewhere, so there must just also be a 2 out front. So now we just have, oh, the antiderivative of 1 over something times the derivative of that something, or again, you can be doing the actual process of u substitution, but you're going to come across with 2 times the natural log of that thing you had in your denominator. And we'll have a plus c. Now, one thing to keep in mind here that's going to be really helpful to us is our log properties. So we often use, right, our exponent properties in reverse like we did in example 3. We also like to use our log properties. The property we get to use here is, hey, I've got a number in front of my log. Remember, you can just move that back up to the top. So we get to call this the natural log of this expression squared. Now, if you're going to square something, doesn't that automatically make it positive? Well, yeah. So you don't need absolute values and squared. It doesn't hurt, but you don't need them. And now it's a little bit easier to see what we can do from here. So the log of something equals the log of something else plus that constant. Well, remember, you can do whatever you want to an equation as long as you do it to both sides. So to get rid of logs, remember, you need exponents. So if we take e to the power of both sides, so if now all of a sudden we have e to the natural log of y equals e to the natural log of that whole thing plus c. Well, good news is that e to the natural log cancels. So the left-hand side, you really just have the absolute value of y equals the right-hand side. Now again, break that up using your exponent properties. So that's going to be e to the natural log of x squared plus 9 quantity squared times e to the constant. And why would we do that? Because e to the constant is just another constant. So we'll have the absolute value of y equals, well, here we've got e to the natural log again, so those cancel out. So we just have x squared plus 9 quantity squared times some constant. Well, let's throw that constant in front. So we have the absolute value of y equals a constant times that expression squared. Well, remember, if you have the absolute value of y, that's just saying, well, okay, it might be equal to the positive constant times x squared plus 9 quantity squared, or it might be equal to the negative whole thing, etc. So there's our final answer. We have solved for y. Now, example 5, this time we're looking for a specific solution again because they give us an initial condition. So at some point in time, probably near the end, we are going to be plugging in that ordered pair. And it's kind of weird for us to see y of 0. They often like to write that instead of just giving us the ordered pair, but don't worry about that. We're just using function notation with f instead of y, but whatever. So we first need to start to separate our variables, yes? So if we have 3 radical x plus 4 radical y dy dx, well, if we just subtract 3x from both sides, we'll have 4 root y dy over dx equaling negative 3 root x. Well, now we just have one more step to get everything with an x on the right and everything with a y on the left. We are going to multiply both sides by that dx to get it to cancel. So we have 4 root y dy equaling negative 3 root x dx. And we integrate both sides, integrating the left-hand side with respect to y, right-hand side with respect to x. And we would have, let's see, so this is really y to the 1/2. So we would want y to the 3/2. We need a 2/3 out front, and we are still stuck with that 4. The right-hand side, we are still stuck with the negative 3, and then it really becomes the same thing. 2/3 x to the 3/2. Don't forget, we have to include that plus c somewhere. Now, our goal is to solve for c eventually, right? Well, again, we could get y by itself right now. It's not going to be super pretty, so let's just plug in that point and see what happens here. So, we are going to have 4 times 2/3 times 10 to the 3/2, whatever on earth that number might be, equaling negative 3 times 2/3 times 0 to the 3/2. Well, if you take 0 to any power, it's 0, times anything is 0, plus a constant, that's just what our constant's going to be. So we can make this slightly better by calling it 8/3 times 10 to the 3/2. Not ideal, but it'll suffice. So then, now that we have c, we need to write our entire equation. So now we are still stuck solving for that y, but it was just a little bit easier to find c beforehand. So let's see, we have 8/3 y to the 3/2 equaling negative, what would that be? Negative 2, cool. Negative 2x to the 3/2 plus that final constant, 8/3 times 10 to the 3/2. Now, as we try to solve for y, one silver lining, we multiply both sides by 3/8, and we distribute it, of course, and it actually ends up canceling with that 8/3 on that other guy at the very end, the fun constant. So, bonus. So y to the 3/2 equals, okay, this is fun, negative 3/4 x to the 3/2 plus 10 to the 3/2. Our last job is to get rid of that fractional exponent. So we're going to take both sides raised to the 2/3. Now, don't be tempted to distribute it in. It doesn't work like that, so we're just going to leave it pretty much as is. So we have negative 3/4 x to the 3/2 plus 10 to the 3/2, all raised to the 2/3 for our final answer. Last but not least, our goal is to find x when y equals pi, given this differential equation, and knowing that y of 1 is 0. So we need to find or solve the differential equation. There we go. So in order to do that, we are going to separate our variables, and it looks like all we have to do is multiply both sides by dx. So it cancels right there, and we just get a y expression on the left. So the cosine of y plus 2 dy is going to be equal to 2x dx. Cool. Antiderivative, antiderivative. Antiderivative of cosine of y with respect to y is just going to be positive sine of y plus 2y, and that is going to equal x squared plus a constant. And we know that y of 1 equals 0. Now, we've gotten in the habit of just solving for c right here, and that's actually extra good news for us because we don't care what our equation is this time, right? We can rearrange and solve for y. That doesn't look overly fun, but we don't even have to because our goal isn't to find y, it's to find x given a particular y value. So let's first find out what that c is, right? Knowing that y of 1 equals 0. So this means we have the 0.10. So we have the sine of 0 plus 2 times 0 equaling 1 squared plus our constant. Well, the sine of 0, let's see, we're over here, that's a y-coordinate, so it is going to be 0 plus 0 is 0 equals 1 plus c, so c is negative 1. So then we know that the sine of y plus 2y equals x squared minus 1. Well, now we can plug in y equals pi. So we are finding the sine of pi plus 2 pi, and that will equal whatever x squared is minus 1, and we want to solve for that x, right? Sine of pi, well, that is also going to be 0. Plus 2 pi equals x squared minus 1. Add 1 to both sides. That equals x squared. And take the positive and negative square root of both sides. So apparently when y equals pi, there are two corresponding x coordinates. The positive square root of 2 pi plus 1 and the negative. So go ahead and do those Khan Academy problems. We will come back together in a couple days here. We're really going to power through as we finish up our